This is CERN, the European Centre for Nuclear Research, but it's best known as the home of the Large Hadron Collider, the biggest and most powerful particle accelerator ever built. It's 100 meters below our feet, 27 kilometers circumference, and it's accelerating particles around, basically trying to emulate the first moments after the Big Bang and the birth of our universe.
When the Large Hadron Collider first started up in 2008, it was the largest and most powerful particle accelerator in the world, and it still is today. Also known as the LHC, it cost about €3 billion to build the machine and counts some 10,000 visiting scientists among its users. At the end of the Collider's first run, scientists at CERN announced they had discovered a particle that resembled the Higgs boson, a crucial part of the Standard Model that had never been detected before.
For me, it's really an incredible thing that has happened in my lifetime.
The Standard Model is a theory that explains the most fundamental building blocks of matter, the basic particles and forces that make up the universe as we know it. Now, the LHC has rebooted for a second run. It's colliding particles at higher energies than ever before. And this time, researchers are hoping to find something that goes beyond the Standard Model. New particles and new physics, something that could revolutionize our understanding of the universe.
We've arrived at CERN just about as it's opening, and now we're getting in our very own CERN car. The Large Hadron Collider is 27 kilometers in circumference, so you have to get around by transport.
The LHC is so large it spreads across the French-Swiss border. One of the main particle detectors on the Swiss side is called Atlas. It's 25 meters high and 46 meters long, hidden in a cavern underground.
This is a Lego version of the Atlas detector, which someone has clearly spent a lot of time on.
This is the Atlas Control Center, where we monitor the detector and can control it. And the detector itself is 100 meters below us at the moment. The LHC has effectively almost doubled in energy from the previous 2012 running to what we're running this year. By moving up in energy, we open this window on producing these heavier, more exciting particles that we've never seen before. The detector itself effectively works like a giant camera. It takes photos of events, and we can reconstruct events, which tells us which particles have been produced in the collision.
So how dangerous is this thing? It sounds like, more energy than ever before, smashing particles.
It's not dangerous at all from the kind of media black hole point of view. The energies of the collisions that we have are much lower than the energies of some cosmic rays that hit the upper atmosphere all the time. If we do discover extra dimensions and things, they're likely to be microscopic. It's not that we find a movement to a parallel world or anything. We're looking at fundamental physics rather than science fiction.
So you're not going to accidentally open a portal to hell?
No, this is not possible at all.
Uncovering the secrets of the universe relies on a mix of experiment and theory. Particle physicists come up with the theories on how the basic building blocks of physics work, and if they're lucky, experimental data might provide evidence they're right. One such theory is supersymmetry, a popular idea that some scientists have been working on for decades, but has so far eluded detection. Affectionately known as Susie, supersymmetry predicts a whole new set of particles to partner the ones we already know about. It's a compelling theory that would solve some issues with the Standard Model and could offer insight into some of the universe's many remaining mysteries, like dark matter. There's just one problem. We haven't found any supersymmetric particles yet.
We're at King's College London to meet John Ellis. He's a British theoretical physicist who splits his time between here and CERN. And one of the things that he's been working on is the theory of supersymmetry. And now with the reboot of the Large Hadron Collider, he's hoping to find evidence that it actually exists.
You can somehow think of supersymmetry as extending our concepts of space and time. What are we? Where do we come from? Where are we going? That is the business of a particle physicist, to at least ask those questions in a scientific way. What are we? Well, we're made of standard model particles. Where do we come from? Well, that's what the LHC is doing. It's banging things together at the highest possible energies. And in that way, we can recreate the conditions that occurred very, very early in the Big Bang. Where are we going? Well, a good question. If you believe the measurements that we made in 2012, the universe is going to collapse. I don't believe that, right? If we want to avoid that prediction, we have to discover some sort of new physics, and that new physics could be, supersymmetry, like the cavalry riding in to rescue us at the last moment.
Wow, it sounds like the stakes are pretty high.
Yeah, we're not pissing around.
Fair enough.
Supersymmetry is a theory that tells us that for every particle that we know, there is another one that we have not seen. It tells us that these other particles are heavier than the ones that we've seen. The lightest one of these particles could be the dark matter that makes up the universe. We're just trying to understand how things got to be the way they are today. And in order to understand that, we have to understand what happened in the very early universe. And the further back that we can go towards the beginning of time, in some sense, then the more we can hope to understand. This year is the 100th anniversary of Einstein's theory of general relativity, which revolutionized our ideas about space and time and gravity. I think the discovery of supersymmetry would be as big as that, something beyond what Einstein could ever dream of.
How confident are you that we will find evidence of supersymmetry?
I would describe myself as being hopeful, but not overwhelmingly confident. We know that the LHC, when it starts collisions at much higher energies this year, is going to have the ability to look for much heavier supersymmetric particles, but we don't know whether the supersymmetric particles are going to be kind enough to be in the range that the LHC can access. I'll be watching the data very, very carefully. But it could be that we will never actually make a supersymmetric particle in the laboratory. We're always going to have to rely on these astrophysical or cosmological or indirect indications.
Wherever we might find evidence, you seem pretty certain that supersymmetry is there to find.
I would say that I am sure that supersymmetry is out there somewhere, because it plays such an essential role, for example, in constructing a theory of everything, and it would help us make a grand unified theory and so on. I don't think that there is any alternative theory that comes close to supersymmetry in terms of how attractive, how powerful, how plausible it is. So if you ask me what would be my backup if we don't find supersymmetry, I'm afraid I'm going to have to scratch my head and say, I don't know. Half of the papers that I've written over the last 30 years I'd have to throw into the bin. But, I'd bounce back. But anyway, I'm optimistic. LHC is about to start up. Lots more energy, lots more collisions. Let's worry about those disaster scenarios when disaster strikes.
The LHC isn't the only machine at CERN. Particles that get that far have to go through a series of other accelerators first. It all starts with a bottle of hydrogen. The electrons are stripped from the hydrogen atoms to leave only protons. These are fed into a linear accelerator before being injected into a small circular accelerator. The particle beam is then directed into another ring, and then an even bigger ring, where it's accelerated further. The protons are injected into the LHC in two beams, one clockwise and one anti-clockwise, and are made to smash together, creating clouds of subatomic debris ready to be analysed. This whole process is masterminded at the CERN Control Centre.
This room controls all the different accelerators that we have at CERN. So we have the injector islands here, so the LINAC and the first booster accelerators. And once the beam comes out of there, it goes into the LHC. So we have beams in the LHC at the moment, and they're looking at optimizing these beams at the moment. It's a busy time. We've just started up, so after 2 years off, everybody's recommissioning all of their instruments.
What actually is the Large Hadron Collider?
The Large Hadron Collider is basically a huge string of magnets, bending magnets, which bend the beam the whole way around in this large 27-kilometer circle. This is basically all it is, a long chain of magnets making the beam going round and round and round. And then at 4 individual points, what we actually do is put an experiment, and there we make these beams collide together. But most of the machine itself, just magnets and a lot of people to make sure that the beams stay where they're supposed to stay.
It's really exciting. It's kind of like the control rooms at NASA when they're launching spacecrafts and everyone's around and waiting. You get a real sense of the amount of work that goes on here. There's so many screens flickering, each with different kind of measurements and stuff going on. And it's pretty weird to know that it's sort of doing stuff right now beneath where we're standing. So why can't we go down there right now?
When the machine is running, in fact, there's no access. The main reason is that we're putting a lot of electrical energy into these magnets. This means that if anything should go wrong, the consequences could be quite major. The other thing is radiation. If the beams are on and we're losing particles, basically we also create radiation in these areas. In fact, if we lose any of these particles, if we lost them all, for example, we would basically destroy most of the LHC. So machine protection is very, very important for us. On the right here we have the main access console. This is all controlled from here. Depending on the situation, there are different keys for the different areas that have to be in a certain position to allow somebody to go down.
Right, so are these actually on-off buttons for the LHC?
Basically, yes.
Cool.
When the protons collide, they produce a shower of other particles that are picked up by 4 main detectors around the ring. Along with ATLAS, one of the main detectors responsible for finding the Higgs back in 2012 was CMS, a 14,000-ton piece of machinery on the French side of the border.
This is like a miniature version of our detector with a slice cut through the middle so we can actually see what's going on. So right in the middle we have the beam pipes that come in from either side. The particles collide right in the center, and then out of the collisions you get loads of, other particles created and debris, and then the whole point of this huge detector is to basically try and identify them, detect them and record them.
Obviously there was a lot of fanfare around the discovery of the Higgs, and that was great for run 1. What would the impact be if we found something beyond the standard model?
The Higgs, we had a general idea how to look for it and where it should be. It formed such a fundamental part of our standard model that the surprise was not that great, I would say. A lot of people expected it. With supersymmetry or any type of exotic search, we're really into unknown territory now. Like, we don't really know. We've got so many theories out there. We're trying to do generic searches where we look at all sorts of different things, but really that would be a massive game changer for the field, because it really would then tell us, a whole new kind of model, a whole new area of particles that we had no idea existed. And that could define particle physics for the next century.
Finding something supersymmetric would be a huge breakthrough, but the problem with searching for new physics is that we're not as sure where to look. And with this second run at double the energy, all eyes are on CERN to deliver results. When he's not in London, you can find Professor John Ellis under a mountain of papers in his office at CERN.
Hi, John.
Oh, hi.
So this is your office at CERN?
Yes.
So looking at your desk, this is quite impressive. Is this what the life of a theoretical physicist looks like?
Well, this is what the life of an untidy theoretical physicist looks like, yes. Or should I say a lazy theoretical physicist who can't be asked to tidy up the desk. I did actually tidy up the desk once, but that was about 25 years ago.
How long have you been working here?
I've been working at CERN since 1973. And in this particular office, I know about 20 years, maybe, something like that. This is the expansion of the universe. So we're somewhere around here. So that's right back at the beginning of the Big Bang. That's a period of cosmological inflation. and the universe is just starting to accelerate again, and we have no idea why. And we're also trying to figure out what actually happened during this phase over there. So there was this new particle discovered 3 years ago, which we think is A, or perhaps the Higgs boson. If you take the properties of the Higgs boson as measured to date, it kind of looks like our universe is unstable and eventually it's going to go boing. Okay, but that could be avoided if the Higgs boson didn't behave in exactly the standard way. So that's one of the things that we're thinking about.
And is this where supersymmetry comes in?
Supersymmetry would be one way of avoiding the future collapse of the universe, yes.
And I can see over here, someone seems to disagree with you. We've got Susie is a lie.
Yeah, but somebody else crossed that out, so at least there's somebody on my side. This was bequeathed to me by a postdoctoral researcher who was working with me, and you can see what happens if people talk badly about supersymmetry.
Are there many people who disagree with you on supersymmetry?
Oh yeah, lots of them. I mean, that's what makes it interesting, right? I mean, it'd be very boring if everybody had the same ideas about what possible new physics we might discover with LHC Run 2. So there's all sorts of different ideas going on.
So is there kind of a bit of a rivalry between theorists there?
Oh, no, of course not. We're all on the same team. Bullshit. Yeah, of course there's rivalry, and that's actually what enables science to progress, when you're bouncing ideas off each other and trying to figure out, in which way what idea is vulnerable and how you can test them experimentally.
Not everyone is as convinced as John by supersymmetry. Just across the hallway is the office of another theoretical physicist, Alvaro de Ruhula. He's more sceptical and thinks some of his colleagues are going a little overboard with their enthusiasm.
On the occasion of the centenary of special relativity, I made a film in which I went to the past and interviewed Einstein.
Dr. Einstein, I presume.
I do not have a doctorate yet. And by the way, that drawing on your chest looks like my grandmother getting out of bed.
The way I did that, going to the past, was to use this helmet and connect myself to plugs in the control room of one of the accelerators here and absorb the energy of antiprotons to generate some anti-time and travel to the past. Of course, that doesn't make sense, but it was only a film. Best case scenario is that the LHC finds something that we absolutely couldn't imagine, because then we would have to understand something else which we know is there and we can study, unlike the dark energy of the universe, which is very difficult to study directly. So I hope there is a surprise that requires new thinking.
Do you think there's a philosophical side to what you do as well as a purely scientific one?
Scientists want to understand things because they can check them. Philosophers cannot check ideas such as ethics. Is this ethics right or wrong? You cannot check that. You can check whether a physics theory is right or wrong, and anybody here or in China or in another planet would reach precisely the same conclusion. That's the meaning of science. It's precisely the opposite of religious faith, which is believing in something that you cannot check.
Do you not think some element of belief has to come into searching for these things that are
I think
unknown?
belief is not a... we speak very often by saying, I believe in supersymmetry. I don't think we should say that. We should say supersymmetry is so convincing that it makes sense to try to test it. But the word belief is very, very dangerous. I don't like it.
Is supersymmetry convincing?
Supersymmetry has a very good assets. It has convincing aspects to it. And for some reason, the theories that are successful in describing nature are always elegant and very simple. We haven't found the elegant and simple way to break supersymmetry.
So is there any kind of rivalry between physicists at CERN?
Yes, people criticize each other openly, often quite intensely. Some people dislike when others get prizes, for instance. There's also envy, not only rivalry. And very many of us think we are much better than we really are. And that also provokes problems because those of us who are like that tend to be unbearable. But we have a referee which is absolute and never makes mistakes, which is nature.
With the collider at the highest energy so far, the pressure's on to find something. And if supersymmetry continues to evade detection, more people will start to question if these particles are even out there to be found. Regardless of what CERN discovers in this run, the search will continue. One idea is to build an even larger collider, up to 100 kilometers long, that could access even greater energies and further expand our knowledge of the universe.
How can you understand the universe today if you don't understand how it got here? I think it's vitally important that we understand as much as possible of the universe about us. Technology, innovation, all these things rely on fundamental advances in science. But what we have to continue doing is pushing back the frontiers of ignorance as far as we possibly can, identifying new questions and finding answers. Often those answers produce new questions, which then become even more interesting, but that's the way it goes.
You read about this kind of stuff and theories of how the universe works, and it's really amazing to see that people are actually experimentally testing this out using this huge piece of machinery. Some people have invested their lives into chasing particular particles, hoping that they'll find them in this run now that they've got more energy. But ultimately, the most exciting thing will probably end up being something that no one expected.